Ladies and gentlemen, welcome to lecture number 3, where we'll be looking at amplitude modulation. This is in a course EEE 4682 Communication Systems. The brief outline of our presentation will look as follows. I'll give a brief introduction to our lecture for today. We'll give the definition of modulation, look at the AM transmitter, and inside there we'll focus on modulation and the modulation, AM modulation, basically looking at high level and low level AM modulation. We'll look at the modulation process, derivation of AM sidebands, power in AM, and finally we'll look at the bandwidth in AM. Now, modulation can be classified in terms of analog and digital modulation. And under analog modulation, you've got amplitude modulation, frequency modulation, phase modulation. While for digital modulation, you've got ASK, FSK, QPSK, and so on. Then in this lecture, we'll focus more on the AM transmitter and look at AM modulation. And then we'll look at low and high level modulation, and then we'll look at the upper and the lower sideband, including power content in AM. Then we'll end with bandwidth calculation for amplitude modulation. By definition, modulation is the superimposition of the carrier signal to the baseband signal. Essentially, this is the process of adding a carrier to a baseband signal, and it is done for the purpose of enabling the baseband signal to travel over long distance. And number 2, to reduce the size of the antenna and to minimize noise and interferences over the baseband signal. Now, the AM transmitter will consist of the radio frequency oscillator. If you look at it in terms of a block diagram, then it also have the baseband coming through the microphone or any other source, and then this will be passed through the audio frequency amplifier, and the two signals mix in the modulator and then go through various stages of amplification before it is radiated in the air. Now, amplitude modulation can be also classified in terms of low level and high level modulation. And under low level modulation, what you basically do is the radio frequency oscillator, initially amplified and put to the modulator. Then you've got also the audio frequency or baseband signal passing through class A amplifier. The two are mixed in the modulator, and then it will undergo a series of amplification until the last stage of the power amplifier, before it is radiated in the air. Whereas in high level modulation, what you do is you get the carrier amplified via various classes of radio frequency amplifiers, starting with class A, class C, and then in the last stage of the class C radio frequency amplifier, that's where you do the modulation of the baseband signal. So modulating signal also is amplified to a higher power level before modulation takes place. And then the modulation takes place in the last class C radio frequency amplifier. And the modulator output is basically an amplitude modulated wave, which can be directly transmitted via the air interface. Now, we've got simple amplitude modulation circuits such as the one given here, and what you notice in this diagram is that you have the carrier signal denoted by RF carrier out input here. This will be mixed with the baseband signal, which is an audio input, and the two gets when the two are mixed in the modulator, and then what you're going to get is the output in terms of the modulated output. And this modulated output is what will then be amplified via various stages. If you're talking of low level modulation, again, figure B also shows the RF carrier input there. Then you've got the audio input, the two are mixed, and then you get the modulated output, which will then be amplified using various stages of linear amplifiers. Again, if you're considering a low-level modulation. Okay, so that's just a basic circuit which you can implement in the lab. However, in practice, you'll notice that the amplitude modulation circuit will be much more complicated, much more intense in terms of discrete components. You'll have more transistor circuits, more resistors, capacitors, basically to maximize in terms of amplification stages that takes place after modulation. Next, I want us to look at the amplitude modulation process. In the process of modulating the signal, what basically does happen there is you have the baseband signal whose amplitude is B, and this baseband signal normally it's of lower frequency, and this baseband is basically superimposed to a high frequency carrier signal whose amplitude is A, and when the two mix in the modulator, you produce a modulated output, which is basically an envelope like this. And this modulated output, one of the interesting things to notice that it's basically, it will carry the frequency of the carrier. The frequency of the carrier remains the same. However, the amplitude of the carrier will change. So in amplitude modulation, what you essentially do is to vary the amplitude of the carrier while keeping the frequency constant. And during that process, you generate an output whose content can be further analyzed mathematically. And this will yield about what we call sidebands. So let's see how these amplitude modulation sidebands are basically generated from the modulated output. Let's consider equation 3.1. Yeah, so it will have an amplitude of A, and then you have and the carrier frequency FC, and then this signal then is superimposed with the baseband signal whose amplitude is B. The amplitude is B, and the modulating frequency, the baseband frequency of A. And then when the two are combined, you are going to have the output, which is a modulated signal as given by equation 3.3, which is basically that equation there. And you notice that in this equation, the amplitude will vary of the carrier. Amplitude of this carrier here will have basically changed by this component, because that component now represents the amplitude of the carrier. So, and in this change, it will have both the amplitude component of the carrier and the amplitude component of the baseband signal together with a sine function. But this can now be further be simplified, and in simplifying this, basically factor out amplitude A, and then in terms of voltages, you're going to get a signal as shown, basically in equation 3.4. So this is still the amplitude of the carrier. This whole portion there representing the amplitude of the carrier being varied. This part is the carrier part, and we can further simplify equation 3.4 by applying the trigonometric identity, which is given below here. And when we apply this, then we're going to get the output of equation 3.4 as shown in equation 3.5. And what you notice is that this will have three components. The first component is the carrier part. The The second component is the lower sideband part, and the third component is the upper sideband component. So you notice also from equation 3.4 that the amplitudes, these amplitudes of the lower sidebands is the same as the amplitude of the upper sideband. And however, in this amplitude, we have a component called M. That M is basically the modulation factor or modulation index, and M is given by the peak value of the modulating signal, which is B, peak value of the modulating signal, which is B, and divided by the peak value of the modulated carrier, which is A. So the ratio of B over A gives you basically what is known as modulation index or modulation factor, as shown in equation 3.6. So equation 3.6 can then be written in terms of equation 3.7, where capital M in this case will be the percentage modulation, and small m being simply B over A, which is the modulation index. So whenever you multiply the modulation index by 100%, it now changes to basically modulation, percentage modulation. Now, from equation 3.5, we can also write the lower sideband and upper sideband frequency spectrum as shown in figure A and B here. You'll notice that in this figure, like I noted, you have MVC over 2, which is basically the amplitude of the lower sideband being equal to the amplitude of the upper sideband. VC, which is the amplitude of the carrier. And down here is indicating the lower sideband being equal to FC minus FA, or the upper sideband is nothing but the carrier frequency plus the modulating frequency. In terms of power relation, you have the carrier power being equal to PC, and then you have the lower sideband power being equal to M squared PC over 4, and this is the same as the upper sideband power, which is M squared PC over 4. Okay. So let's look at the power content in AM. Since power is proportional to the square of the voltage, the power versus frequency spectrum for an amplitude modulated wave looks as shown in the previous figure. And we can calculate the total power both in the upper and the lower sideband, and also the carrier part, which will be given by equation 3.8. And if you look at this equation, essentially you'll have the power component due to the lower sideband here, the power component due to the upper sideband power component, and then you have got the power component due to the carrier to give you the total power. Now, from equation 3.8, we can add the upper and lower sideband power to yield equation 3.9, where M squared PC over 2 is nothing but the summation of our upper sideband power and the lower sideband. Then you have the carrier component being dropped here to form equation 3.9. And if we factor out the PC here, you have PC being out of the equation, and then you have 1 plus M squared over 2 to yield equation 3.10. So equation 3.10 now is a summarized version of the total power in both the upper sideband, lower sideband, as well as the carrier. Let's finally talk about the bandwidth. This bandwidth can also be calculated, and we know from the definition, bandwidth is basically the difference between the lower frequency and the highest frequency. So if I know, simplifying this equation, we're going to have FC plus FA minus FC plus FA. Then simplifying this further, this will subtract with that. Then you're going to have FA bandwidth. So in some books, FA is usually denoted as FM. So basically be equal to FM. That is basically what we have here in calculating your bandwidth. So, these are some of the references that I've used. These are a few tutorials I would want you to try. Question 2 up to 3. This marks the end of our presentation. Thank you for listening.